this model will help us to analyze transformer circuits. Oh, that's what we're going to do, hopefully today. Last lecture that each winding of cover wires with resistance. So side one R1 and R2. Go in the core, but some flux, they are not linking the other winding for the leakage. I represent this by XL leakage reactance. Single wall, because we have many X's, many reactants. So we have one is the leakage reactance. Leakage reactance of winding. And in the middle, you have the ideal transformer. What for E2 equal I2 over I1 equal A, the turns ratio. But once we add the resistance and so we have non-ideal model, and the one inside the core with the winding, this is the ideal model. So we added the resistance and the reactance to make it a little bit more practical. So when you look at the equations, because we're going to solve today many problems, and you're going to solve problems. So pay attention how we're going to do the analysis. When you look for the first equation here, that's normal. That's we know the voltage of winding 1 over 2 is equal to resistance in 1 over N2. And we said that the current has a different relationship that would be the opposite. E1 the voltage, because we have non-ideal model. They are different now. When it was this impedance. The same thing for E2. So now we are talking about non-ideal. When you go for find the equation, what's the voltage V1 here? V1 will be equal E1, the EMF, plus the drop across this impedance. If you want to find the voltage V2, will be the same thing. Will be the voltage E2 minus the drop, right? Because the direction of the current will be in this way, right? So the subline here, so V1 is greater than E1. So V1 is equal E1 plus the drop. But V2, the output voltage on the secondary will be equal E2 minus the drop. All right. How you find the power? How you find the power? Well, and the output, which is V2, not E2. There was a single phase power. How you find the input power? The input power is at the supply. You have the supply voltage V1 and the current produced I1. Let me just write in this arrow I1. And this is I2. So if you want to find the power by the source, you multiply V1 vector I1 conjugate and then find the real part. It give you the power input. If you want to find the output power, P output, you find the voltage at the load, which is equal V2, multiplied by the current conjugate, I2 conjugate, and then find the real part of this to give you the output power. Divide the output by the input power, you get that efficiency. Right? So that's the non-ideal model. But you got RC1 and you got JXN1. What does it mean? It means even if you don't, there is a current going through the coil, and since the current through the coil, there is flux in the core and starting to build things. And due to the history, there is eddy current, all the things. So not to get involved in everything. Now we have two X's, two reactances. Remember, X1, X2, that's the reactance of the winding itself. X actual reactance or magnetizing reactance. Magnetizing reactance that's responsible for building the magnetic. And since the magnetic field alternating and linking with some kind of iron core, it will be loss, eddy current, and hysteresis. So that's the loss. So RC core losses represent the loss of the core, and XM represent the magnetizing reactance, and in parallel. Okay. So now, if you do then the other one, that is the simplest thing. And as engineer, usually when you want to get the first impression about the circuit, get the numbers first to see, we have feeling of it. Then when we want to go in more detail, then we go and look at this one that include the no load loss in the transformer. Case, you will see that, let me just, I have sketch nicer than that. So in the middle here, what you have, this is the ideal transformer, E1 and E2. And then you added impedance of the winding 2. You add impedance of winding 1, and you add the parallel branch representing no load, the transformer. When you are analyzing the secondary or winding 2, there is no change than the what I mean first time. I mean by when we did the first circuit, there is no change because you don't have the branches or anything. It's the same, but the change will happen on this side. Why? Because you have I1 now. The I1, it's the primary current. It's divided at this junction into two currents, IB and I5. And IP, by the way, you can call it, you can make it I2 dash. Why? Because I2, if you transform it by the ratio A, you will go here, you call it I2 dash. Many textbooks use that, and I like that. But here they used IP. See, I'm trying to say that's the current, the primary winding. It's okay, but it's the value, it's I2 dash. Let me refresh your memory how you get I2 dash. We know that E1 over E2 is equal what? Don't forget this one. I2 over I1 equal A, and A is the turns ratio. Don't forget N1 over N2. So that's I2. That's I1. The equivalent of I2 on the other side, we call it I2 dash. So what's I2 dash? I2 dash is equal I2 divided by A. So if you know I2 dash, I'm sorry, if you know I2, which is the load current on the secondary side, divided by the turns ratio A, you get the corresponding current on the primary side. So now in this circuit, I1 is equal I2 dash plus I5. What's I5? It's called exciting current. And exciting current, I5, is divided into two currents. One going for the core, loss resistant, and the other one going for the magnetizing reactance. It's nice always to talk, but we have to make a numerical example. But before that, this circuit, when you solve it like that, on the primary side will be a little bit mathematically complex. Because you got to find the voltage here across and the current. So the engineering always try to simplify it if it is reasonable. So I put for you here assumption, not assumption. That's what's happening exactly. First of when they designed the transformer, they tried to have loss. They don't have big loss because that's not efficient. So they designed it in a way with material, with the core, that it's the loss, the core loss is minimum. So if the core loss is small, so what do you think about the resistance that representing this loss, RC? I will ask again. They, as engineering, would design the transformer in a way that the core loss is RC. So RC, the core loss resistance, what do you think? Value or small value? Small value? Large value? Why? Power. Watch this. Power is equal V square over R, right? So if you have power equal V square over R, and remember, we try to its power loss to make it minimum. So what's R equal V square over power? Is minimum. You want to keep it minimum. So what's R? Of the winding, it's ohms. So R has big, it's a high value, has a high value. So it's like always in kilo ohms. All right. So that's number one fact. So we'll say, so what is the value? Or not the big value? When you go back to the equivalent, if R has a great value, so what's the current? I want to move it someplace else. What about X? Do you think XM is big or small? Does it have a great value or small value? If you say XL is big, it means that L is big. Why L has a great value? If you say the reactance has a great value, so means the inductor, because X equal omega L. Omega is fixed, so it means L. So why L M is big? You got to review what we did in magnetic circuit. What's L? Can you design L? We did that design equation. L is equal what? Mu, right? N square A over L. So it's proportional with mu. U means the permeability of the core. So XM is proportional to L, the inductance, and the inductance was proportional. What do you think? The permeability has a big value or small value? Guys, magnetic circuit. I reviewed. You got it in physics. What's permeability? What is the value? No, I'm talking new of the core. Yes. Yeah.
The core constant.
High value?
Well, yeah, because it's a denominator, so
why won't the mu of the core have higher value?
Because since mu is
I'm not talking about math, about physically. Why won't the permeability to be big?
you're gonna get more current or power.
Mobility doesn't give current. Mobility, it relates the magnetic field, right? What's the relation you know about mu in magnetic field?
B equals
Exactly. B equal mu times H. What's B?
B is flux density.
Flux density. It means that if you have the area, it also the flux. So this is what's going in the pool. So you want the flux, there is to be high or low? High. So how we make it, if H is fixed, we have specific current, you have specific H, you multiply it by mu. So if mu is high, B will be high. Magnetic field will be high, and that's what you want. Yes. Is high. If the inductance is high, Xm is high. And if Xm has a great value, so the current Im through this inductance is going to be very small. So the current in the cool loss resistance is very small. The current through the reactance is very small, Xm. So the total current, exciting current I is very small. So actually, if you look for this one, it will be like, if you have current like 5 amp, so this exciting current will be like 0.1. So the current will be going here. The difference will be 5 minus 0.1, be 4.9. So it's not affected. So is it okay? Since this is fact, what about if we get this branch and we move it toward the supply? That will make life easy. They did that. They move it towards the supply. So that's the approximated non-ideal transform model that you are going to use it all the time. You are the first one at the top. Because it makes math easy when you're doing the calculation. Yes. Supply. So you want to find the current, divide the life is easy. So that's what we're going to do. Let's now take one example. I already put the lecture on the Fourier system, so you can follow. That's the example we're going to use. And that's the data given, 23 kilovolt amp, 2300 to 230 volt, step down. So that's, we call it V1, and that's, we call it V2. And the frequency 6 hertz. The parameters of the transformer are given, R1 and X1, the resistance and the reactance of the winding 1, R2, X2, the resistance and the reactance of winding 2, RC1, XM1, the cool loss resistance and magnetizing reactance, refer to the primary side, refer to 1. What does it mean? Yes, you can make the test on the other side, the secondary, you can make it in the primary. So when you say RC1, it means on side 1. All right. Now, what's required? It's required to calculate the efficiency of the transformer. When there is load across the secondary, the transformer is operating at 75% of the rated load, and the power factor is 0.866 leading. Okay, so let's just think about it. What's required? Efficiency. You said that the efficiency, how you get the efficiency? Power output divided by power input. That's the efficiency. The definition of efficiency everywhere, mechanical system, electrical system, it's the output power divided by the input power. How you find the output power? You got to have the voltage and the current at the output. So you need the voltage at the secondary, V2, and you need I2. You want to calculate the power input. So what you're supposed to get? You're supposed to have V1 and I1. So now we know what we were supposed to. Yes.
What's the formula?
The power V times I conjugate, it will give you the complex power, real part, and imaginary power. If you take the real part, that's the power, the active power.
So it'll
Times I2 conjugate, yes. Okay. Yeah. So let's just get the output power first. We need to get V2 and I2, right? V2, what's the value of V2? Exactly, 230 volts. Okay. What about the current? Three kilovolt amp, yes.
divided by 230.
Exactly. But that will give you the rated amp. What does it mean I accepted? The first lecture on transformer, when you say the rating of the transformer, they give you the apparent power, which is given here. That's S. They give you the input and the output voltage and the frequency. So if you have the rated power or apparent power, you have the voltage, you can get the current, rated current. But they are not working on 100% of rated load. They are operating on 75% of the rated. So first I get the rated load, as you said, divide the apparent power by the voltage, get the current, and then multiply by 0.75, I get the load, right? Because it's operating on 75%. So let's just go ahead and do that. So we'll say that the current, know that S equal to is equal, all right, 2, 3, 0. Volt amp. Of course, doesn't matter the S input or output, because both are the same. 2, it's given 230. So I rated value, it's equal S. This is also the rated value divided by voltage rated V2. So you got 23000 divided by 2, 3. What you get? You get 100 amp. But the current at the load, we call it I2. It's equal 0.75 times the I rated value. So it will be equal 0.75 times 100. So the current is equal 75 amp. Got the current? No, we just got the magnitude. We need to find the angle of the current. It's given that the power factor is equal to 0.86. Let me just write. The power factor is equal to 0.866 leading. Power factor. Power factor is equal cosine phi. What's phi? The angle between the voltage and the current. Yes. It said in the problem, let me show you the problem, what they said. It was mentioned that transformer is operating at 75% of its rated load. That's given, yeah. So it means if you have the voltage in this, that's voltage V2, and the leading current, it means that the current will be in this direction, right? That's I2. And that will be the angle phi. How we get phi? Phi will be equal cosine minus 1.866. That will give us 30 degrees. So now we can write that the current I2 as a phasor is equal I2 magnitude 75 amp and the angle 30 degree amp. So that's the current. We got the first thing. That's great. Can I get the output power now? Yes, you can get the output power. What's the power? The power output is equal the real part when you multiply V2 I2 conjugate. The real part of the voltage is equal to, assume angle 0, and the value of the voltage at the secondary 230 on angle 0. And the current conjugate, how you do the conjugate? Just change the sign from positive to negative. So you have 75 on angle negative 30. Multiply and then get a complex number, and then get I got the real part. It's equal to 14,938.94 watt. The real part only. That's why I'm concerned. did the out. Now we want to find the input. In the problem, they said, do this problem 2 times. One time when you're ignoring the parallel branch that's expressing the no load loss. And secondly, when you include. So let's just do the easy one. First, let me just put this. That's the simple one, doesn't have the parallel branch. Find V1. V2, we know it's equal to 230 voltage. We got the current I2 as a phasor, 75 angle 30. Right? We have R1 and X1. The value of R1 and X1, and R2 and X2, sorry, first, R2 and X2. That was 0.04, that's R2. And X2 was 0.12. Boom. So I have this. Let me ask you a question. How can you find V1? That's the information that you have. Of course, you have the turns ratio. It's step down. I think it's 10:1. So that's what we got. So how you find V1? V1 is on the other side, right? That's the circuit. Let me make it bigger here. That's V1. How you find V1? You have to have I1, right? What do you need? You need I1. About R1 and X1, you are given. Let me give you the value that R1 and X1. R1 is equal 4 ohm, and this one equal to 12. So that's the information that you have. You want to find V1. What you do? What power?
The rate power.
Or is for the load. You didn't mention anything. We need to calculate the input power. That's want to see or seeking that. Yeah.
Current times
You mean by I1, right?
I1 equals I2 times like.
Yeah, okay. So I understand you. So what you're trying to say that I2 you converted. Multiplied by the impedance, okay, and then I1 times 4 plus J12, right? There is ratio, exactly. You use one has to be related to E2. So we have to calculate E2, right? Can you calculate E2 from the circuit? This circuit A, E2 is equal what? The current is in this direction. It may drop like this one, and this is the plus 9. So E2 is equal the voltage V2 plus the drop I2 times the resistance 0.04 plus J 0.12, right? You have I2, you have V2, you get E2. So we got E2 equal to, it would be like a phasor also. It's equal to 8.287, and the angle is 2.33 volt. I got E2. Why I got E2? Because I want to get E1. What's the E1 and E2? A. E1 over E2 is equal A. So now we can get E1 is equal A times E2. A1 is equal 10, and E2, you have it today. You have, you just multiply it by 10, you got 282.87 and the same angle, of course, 2.33 degree volts. You got E1. Why I was trying to get E1? I want to try to get E1 because I want to solve for V1. What's V1 here in this equation? V1 is bigger, so because the drop positive, negative, so it's equal E1 plus the drop I1 times 4 plus J12. Okay, so let's just have V1. Well, I'll write the equation again. E1 plus the current I1 times 4 plus J12. Okay. Well, now I have E1. We got it. This is the value of E1. 2282.87 plus I1. I don't have I1, but I got I2. What is I2? I2, it's here, 75/30. So let me just write on the side here, I2 is equal 75 amp on angle 30 degrees. So I1 will be equal I2 divided by A, opposite to the voltage. So it means I'm going to divide it by 10. So I have 7.5 and angle 30 degree amp. So you have 7.5 on angle 30 multiplied by this impedance 4 plus J12. And if sometimes you forget the formula, I'm going to divide or multiply and do the current. That's very easy, very simple. I always divide. If I'm going on the other side, yes. All right. So now we got V1. If you add it, you get V1 equal 2.578 and the angle 4.7 degree voltage. That's the voltage. You are ready now to calculate the input power. Why? You multiply V1 by I1 conjugate and then find the real part. It will give you the input power. So the input, yes.
There was the question, what's
The value of what?
of V2?
The value of V2, it's the rated value from the beginning, that 230 volts on angle 0. That's the, yeah. So when you calculate the input power, you got the real part, and V1, we got it already here. You take all of it as a vector, 578, and the angle 4.7, times the conjugate of current I1 will be 7.5, angle negative 30. You just use the calculator, get the real parts. Out of it, that will be like 15, 389.14 watt. You got the input power. Now we can calculate the efficiency. The efficiency is equal the output over the input. And when you did it, if you wish, you can multiply by 100, and I got 97.1%. This problem should be done also using the branches in the middle, RC and XM. I will leave it for you, and I will put the solution after you do it. I will put the final answer for it. Because now I want you to work on a problem that I give you the sheet. So every 2 members in every team, they should have the sheet. And I will read it. You should finish it before the class time. Do you have enough time? Yes. You have like 16 minutes. 2 in each one. The problem here, you have I made it easy for you. I give you the amp of the low. I corrected. It's 75 on angle. An angle negative 30. All right. And I am giving you the resistance and everything. And by the way, there are steps to the left in the box to help you. If you look, arterial steps first, find turns ratio, you do turns ratio.